In calculus, a commonly used technique is the power rule. The power rule is used to find the derivative of a power. The derivative gives us the slope of the tangent, which is the instantaneous rate of change at a given instant. In general terms, the power rule states that the derivative of x to the nth is n times x to the exponent n minus 1. The derivative of a constant, meaning that the base is not a variable such as x, is always 0 because obviously there is no change in a constant, so the slope is always 0. You could also show that using the power rule. Let's say f of x equals 5, which is a constant. That can be rewritten as 5 times x to the exponent 0 because x to the exponent 0 is 1. So then you would have to bring down the 0 to be the coefficient of the power and set the exponent to be 0 minus 1. That would be 5 times 0 times x to the exponent negative 1, which is just 0. So when deriving a constant, you'll always have to bring down a 0 from the imaginary x power, which will set the derivative to be 0. The derivative of a linear function is always just the slope, which is a constant, because on a linear function, the function value is always changing uniformly by the slope. We can show that using the power rule as well. So let's take the typical linear function and say y equals mx plus b. When we take the derivative of that, the b will just be 0 as we were just discussing, it's a constant. And we take down 1 from the exponent on the x, and then subtract 1 from 1 in the exponent. So that will always leave us with y prime equals m, which is the slope, times 1, times x to the exponent 0, which is always 1. So y prime equals m, so y prime equals the slope. Keep in mind, if you're finding the derivative of a function with multiple terms in it, you would just find the derivative of each term and keep them separate, but still add or subtract them just as it was in the original function. So if it's a standard polynomial, you would just use the power rule on each term and add or subtract them as they were. I'm going to go over some examples now. Find the derivative of f of x equals x. Well, you can rewrite that as f of x equals x to the exponent 1, then just bring the 1 down and the exponent will be 1 minus 1, so it'll be 1 times x to the exponent 0, which is 1, so the derivative of the function f of x is 1, which is a constant, so at any point on the graph, the instantaneous rate of change is 1, or 1 unit per interval. It makes sense because if you look at the y equals x graph, the slope is constant at 1. If x equals 5, y equals 5 as well. If x equals 6, y equals 6. It's always changing by just 1 at any point. Find the derivative of the function f of x equals x cubed. So bring down the value of the exponent, 3, to be the coefficient to the power. The exponent will then be 3 minus 1. So the derivative of f of x equals x cubed is 3 times x squared. Now let's try finding the slope of the tangent at a given point on a function. The first thing we have to do is find the derivative of the function, which we know already is 3 times x squared. Then we have to sub in the x value of the point into the derivative function. So we sub in x equals 3 and the y value doesn't matter. When we sub in x equals 3, it will equal 3 times 3 squared, which is 3 times 9. That will give us 27. So the instantaneous rate of change at point 327 on the function f of x equals x cubed is 27 units per interval. It's just a coincidence that the slope of the tangent is the same as the y value of the point. I'll now sub in the point 28 to the same function to prove that it is just a coincidence. You'll get 3 times 2 squared, which is 3 times 4, which is 12. So the instantaneous rate of change at point 28 on the function f of x equals x cubed is 12 units per interval, which is not the same as the y value at that point. So this is finding the derivative of a quadratic function. For the function h of t equals 65 plus 3t minus 5t squared, where h of t is the height in meters and t is the time in seconds, find the exact rate of change at 3 seconds. All you have to do is find the derivative of the quadratic function and then sub in t equals 3 seconds. Firstly, I rearranged the equation to look better, so use the power rule on each term in the quadratic to get the derivative. On the negative 5t squared term, bring the 2 down to be the coefficient to the power and subtract 1 from 2 in the exponent. On the 3t term, you'd bring down the 1 and subtract 1 from 1 in the exponent. And finally, on the third term, 65, it's a constant, so you just set it to be 0, which eliminates it. And then your final derivative simplifies down to h primed of t equals negative 10t plus 3. So now just sub in t equals 3 seconds into the derivative, and you'll get negative 10 times 3 plus 3, which is negative 27 meters per second. So the instantaneous rate of change at 3 seconds for the function h of t equals 65 plus 3t minus 5t squared is negative 27 meters per second. Then, for the same function, find when the object reaches its maximum height, which is when the instantaneous rate of change is 0 meters per second. And that's because for a turning point, the instantaneous rate of change is 0. It's also quadratic and opens down, so it only has one turning point, which is its maximum. We already have our derivative, so now just sub in h prime of t equals 0, so the instantaneous rate of change is 0, and solve for t. So 0 equals negative 10t plus 3, subtract 3 from both sides, then divide both sides by negative 10, and you'll end up with t equals 3 over 10 seconds, or 0.3 seconds. Therefore, the object reaches its maximum height at 0.3 seconds. Find the derivative of each function. The first one is f of x equals 4 divided by x cubed. You can rewrite that as 4 times x to the negative third, and then find the derivative using the power rule. So bring down the negative 3 to be the coefficient of the power, the same as 4, and then subtract 1 from the exponent, and you'll end up with negative 12 times x to the negative fourth. You can then rewrite that to be negative 12 divided by x to the fourth. The second one is g of x equals negative 12 times x to the exponent 0.25. Just like if it was an integer as the exponent, you bring down the 0.25 to be the coefficient to the power, and then set the exponent to be 0.25 minus 1. That will then simplify down to negative 3 times x to the exponent negative 0.75. You can then rewrite that so that the exponent on the power is positive, and it'll be negative 3 divided by x to the exponent 0.75. We also know that 0.75 is 3/4, so we can rewrite it as negative 3 divided by x to the exponent 3/4. And finally, we can rewrite the power as a radical, so the final answer could be g primed of x equals negative 3 divided by the 4th root of x cubed. For the final example, we're going to derive a function with multiple terms in it. We have the function f of x equals 5x to the 4th plus the cube root of x squared plus 2 over 3 times the square root of x minus 7x to the exponent 1/2. The first step is to rewrite the equation with the radicals as powers and factor out coefficients where necessary. So the first term isn't changed, but the second term is rewritten from the cube root of x squared to x squared to the exponent 1/3. In the third term, we just need to factor out the 2/3, and we're left with 2 over 3 times 1 over the square root of x. And the fourth term is left alone. Next, we're just going to rewrite the second term from x squared to the exponent 1/3 to x to the exponent 2/3. And the third term is rewritten so that 1 over the square root of x is x to the exponent negative 1/2. We want to have powers be in the numerator. Now we can start calculating our derivative function using the power rule on each term in the function. So bring down the 4 and subtract 1 from the exponent. That will be 5 times 4 times x cubed. Then bring down the 2/3 to be the coefficient to the power and set the exponent to be 2/3 minus 1, which is negative 1/3. Then bring down the negative 1/2 and set the exponent to be negative 1/2 minus 1, which is negative 3/2. On the final term, bring down the 1/2 and set the exponent to be 1/2 minus 1, which is negative 1/2. 5 times 4 times x cubed simplifies to 20x cubed, and that term is now done. 2/3 times x to the exponent negative 1/3 can be rewritten as 2/3 times 1 over the cube root of x. When multiplying 2/3 by negative 1/2, the 2's will divide out and you'll be left with negative 1/3 for the coefficient to the power. X to the exponent negative 3/2 can be rewritten as 1 over x to the exponent positive 3/2. And you may or may not choose to write 7 times 1/2 as 3.5, but the power of x to the exponent negative 1/2 should be rewritten as 1 over the square root of x. We are rewriting the equation back in radical form where appropriate because we're coming to our final solution and we don't need to keep fraction exponents anymore to use the power rule. So 2/3 times 1 over the cube root of x can be rewritten as 2 over 3 times the cube root of x, and that term is now done. Negative 1/3 times 1 over x to the exponent 3/2 is negative 1 over 3 times x to the exponent 3/2. And then the last term's coefficient can be rewritten as 7 over 2 instead of 3.5, like it probably should be. And then for the final step, the first two terms are done, and the third term can be subtracted now instead of added because the numerator is negative, and the 3 times x to the exponent 3/2 can be rewritten as 3 times the square root of x cubed. The last term is equal to 7 over 2 times the square root of x, and that is your final derivative. The derivative of the function f of x equals 5x to the 4th plus the cube root of x squared plus 2 over 3 times the square root of x minus 7x to the exponent 1/2 is 20x cubed plus 2 over 3 times the cube root of x minus 1 over 3 times the square root of x cubed minus 7 over 2 times the square root of x. In summary, the first step is just to rewrite your initial function with powers instead of radicals and possibly factor out coefficients where needed. Then just simplify the rewritten function as much as possible and make sure that the powers are in the numerator. After that, use the power rule on every term in the function and then just simplify the result from that.